Today we're going to look at the strange and unsettling topic of rearranging conditionally convergent series. And this is treated a lot of different places, but we're going to mostly follow some notes from a talk by Chris Cohen that I found online. You can find these fairly easily. Okay, so let's start with some facts. And that is, well, a series is called conditionally convergent if it converges, but the series containing the absolute value of its terms does not converge. Then here's another fact. A conditionally convergent series can be rearranged to have any sum. So we won't prove that here, but perhaps we'll do that in an upcoming video. And here's some other specific facts regarding the alternating harmonic series, which will be the series that we're studying today. First of all, if you do not rearrange at all, so you have 1 minus half plus third minus quarter plus fifth minus sixth, so on and so forth, the sum of that series is the natural log of 2. Whereas if you have this pattern of 1 plus and 2 minuses, 1 plus and 2 minuses, forever and ever and ever, like 1 minus half minus quarter plus third minus sixth minus eighth plus fifth, so on and so forth, you get a value of 1/2 natural log of 2. We won't prove those, but we will prove something similar as well as a very general result for which these will be a special case of. And so our main goal for today is to investigate a rearrangement that includes m pluses and then n minuses repeated over and over and over. And we're going to start with a bit of a warm-up problem, and maybe it's like the cousin to this second rearrangement, which is what happens if we have 2 pluses and then 1 minus, 2 pluses and then 1 minus, and so on and so forth. Okay, so our strategy will be first to employ something called Abel's theorem, which allows us to write the sum of any convergent series as the limit of a power series. And what we'll do is write this as the limit as x goes to 1 from below of x plus 1/3 x cubed minus, so you might think I'm going to do minus 1/2 x squared, but I want to keep the powers of x in an increasing order. So I'll put minus 1/2 x to the fourth, and now they're in an increasing order. And then I'll have plus 1/5 x to the fifth, plus 1/7 x to the seventh, minus 1/4 x to the eighth, because I need that in an increasing order, and then so on and so forth. So a 9th x to the 9, an 11th x to the 11, and then finally minus 1/6 x to the 12th, and so on and so forth. Okay, good. But now let's notice that if my limit is x going to 1 from below, then that means everything in here is converging absolutely. And you can check that fairly easily. But since everything in here, inside the limit I should say, is converging absolutely, that means it can be rearranged. So I'll rearrange it so that all of the positive terms are grouped together and all of the negative terms are also grouped together. Well, that's not exactly what it's going to be, but that's pretty close to what it will be. And I should reiterate here that the important step from here to here requires these powers of x's to be increasing. So that's important. And that is, essentially why this rearrangement is legal, because we have a legitimate power series here. So we have the limit as x goes to 1 from below. And then, well, here's the grouping that I'm going to do. I'll group each first positive term with each first positive term. And then after that, I'll group each second positive term with each second positive term. And then finally, I'll group all of the negative terms together. So it's not exactly grouping all of the positive terms and all of the negative terms. It's like grouping them in this pattern. Okay, so let's see if I can color code this. So I'll put everything underlined in orange with orange parentheses. So I've got x plus 1/5 x to the fifth, and then plus 1/9 x to the 9th, and then so on and so forth. And then next, grouped in these red parentheses, are all of the second positive terms. So that'll be 1/3 x cubed, and then let's see, 1/7 x to the, that should be 7 there, oops. And then finally 1/11 x to the 11th. And then that's gonna continue on and on and on. And that should be red parentheses. And then I need to subtract off the negative terms. So those are gonna be grouped in blue parentheses. So I've got 1/2 x to the 4th. And then next up is 1/4 x to the 8th. And then 1/6 x to the 12th. And then so on and so forth. Okay, so that's shaping up. But now I'd like to sum that up. And in order to do that, I'll notice that if I take a derivative, then I have geometric series. So I'll take a derivative and an antiderivative simultaneously. So this will be the limit as x goes to 1 from below. And then I have the antiderivative of all of that stuff where I have taken the derivative. So let's maybe go ahead and use our color coding again. So this is going to be 1 plus x to the 4th plus x to the 8th plus, you can guess the next one will be x to the 12th, so on and so forth. Okay, good. And then plus, taking the derivative of everything in red, you'll see that we have x squared plus x to the 6th plus x to the 10, so on and so forth. And then minus, taking the derivative of everything we have in blue, will be 2x cubed plus 2x to the 7th plus 2x to the 11th, and so on and so forth. Okay, so I think that's looking pretty good so far. But now I can sum all of those geometric series just using the standard rule for summation of geometric series. So I have the limit as x goes to 1 from the left, and then I have the antiderivative of, let's see. So this geometric series in orange will be 1 over 1 minus x to the 4th. So I think that's pretty clear because my starting term is 1 and my common ratio is x to the 4th. And then to that, I'll add the sum of the geometric series which is occurring in red, which will be x squared over 1 minus x to the 4th. Okay, and then finally that geometric series is happening in blue will be subtracted. So my starting term there is 2x cubed, and then my common ratio is x to the 4th again. So that's over 1 minus x to the 4th. Okay, so that's the kind of situation that I have right here. I need to take the antiderivative of that object and then take its limit. Okay, so let's maybe move that up. So I've taken what we had on the last board and I've done some minor adjustments, and that's just really doing arithmetic on those rational functions. So now I have half the limit as x goes to 1 from below, the antiderivative of 1 over 1 plus x plus 1 over 1 minus x minus 4x cubed over 1 minus x to the 4th. And now we're pretty much set up. So now we have 1/2, and then the limit as x goes to 1 from below. So the antiderivative of 1 over 1 plus x is simply the natural log of 1 plus x. So that's pretty straightforward. So the antiderivative of 1 over 1 minus x will be, well, it's going to be a natural log again, but now we will pick up a minus sign because of the chain rule. And then notice that the derivative of the denominator here is essentially inside of the numerator. So via a u substitution, that'll give us plus the natural log of 1 minus x to the 4. Okay, nice. So that's the object that we need to take the limit of. Now we can start putting this together using logarithm rules. So we'll have 1/2, and then the natural log of x goes to 1 from below of the natural log of, let's see what we have, 1 plus x times 1 minus x to the 4th over 1 minus x. Next up, let's use the kind of standard factorization of 1 minus x to the 4th. That'll factor as 1 minus x times 1 plus x squared plus x cubed. So now we can take this 1 minus x, cancel it with this 1 minus x, and then take the limit as x goes to 1 from below. So that'll give us a 2 right here and then a 4 right here. So we'll have 1/2 the natural log of 8. But 8 is 2 cubed, so perhaps we could really write this as 3/2 times the natural log of 2, which is like a nice form, and it's like kind of in line with what's going on over here. Okay, so now that we've done this nice warm-up problem, let's look at our main goal. Now we're ready to look at the general case, but before we do that, I'd like to recall a fact, and we've looked at this in a previous video. And that is that if you take the limit as k goes to infinity of the partial sum of the harmonic series, so 1 plus half plus third all the way up to 1 over k minus the natural log of k, well, that limit converges to a number known as the Euler-Mascheroni constant, which is called gamma. Furthermore, there's some nice notation here where h sub k is this partial sum. It's known as the kth harmonic number. I've collected these values of rearranged alternating harmonic series that we've seen so far down here. So I think it's interesting that they all involve this natural log of 2. Okay, so let's get to our main result here, which is what if we do some sort of alternating setup, or some sort of rearrangement, I should say, where we've got m positive terms followed by n negative terms, followed by m positive terms and n negative terms, so on and so forth. So here are the first 2 blocks. So the first m positive terms would be 1 plus third all the way up to 1 over 2m minus 1. And then the first n negative terms would be 1/2 plus a quarter all the way up to 1 over 2n. And then we pick up with the second block of each. So our strategy here will be to write this as a limit of partial sums. So let's write this as the limit as capital N goes to infinity of, well, let's maybe start this thing out. So we'll have 1 plus third all the way up to 1 over 2m minus 1. And then we want to step back and ask what capital N counts. So capital N is going to count the number of our blocks. So if n is equal to 1, it would just be this term right here. If n is equal to 2, it would be everything on the board. If n was equal to 3, it would include the next 2 terms. So the positive block and the negative block. So if we've got n positive and n negative blocks, I think it's easiest to write down the negative block. So here we've got minus, and then I'm not going to worry about all of the first terms, but notice the last term is 1 over 2 times little n times capital N. So that's following the pattern that's being built on the board. And then what about the nth positive block, the capital Nth positive block? But I'm not going to worry about the first terms. That will end with 1 over 2 little m n minus 1. So that follows the pattern that's going on here as well. Okay, and then we've got all of that stuff in the middle. Now what I'd like to do is smash all of these together into all of the positive terms together and all of the negative terms together. And I can do that inside of the limit because I've got a partial sum in the limit. That's a finite sum. I can always move things around if I have a finite sum. So that'll be the limit as I still have my capital N goes to infinity, and then my positive terms. So that'll be 1 plus 1/3 plus 1/5 plus 1 over 2 little m capital N minus 1. So those are all my positive terms. So notice they've got odd denominator. And now let's subtract off all of my negative terms, which they have even denominator. But since they have even denominator, I'm going to take advantage of that to factor a half out. So that'll be minus 1/2, and then we'll have 1 plus a half plus ending at 1 over little n times capital N. That would be that term right there. Oh, but let's look at this carefully. This is exactly a harmonic number, which is good because we're going to use this in the future. And so which harmonic number is this? This is h sub n capital N. Okay, nice. So now we'd like to write this sum of reciprocals of odds into a harmonic number as well. But the only way to do that is to build it out by adding all of the reciprocals of the evens that we are missing. So let's do that here. So we're going to add 1/2, and then we'll add 1/4, so on and so forth, into this like next to last term, which will be 1/2m capital N. But now if we've added all of those in, that means we also have to subtract them. But let's take 1/2 out of each one because they're even. Well, the denominator is even. So that means we're subtracting 1 plus 1/2 and then ending at 1/m times n. Okay, great. And now let's observe that we've created another harmonic number here. This is h sub mn, and a harmonic number here. So this is h sub 2m capital N minus 1. So that's kind of a gnarlier harmonic number, but I think that's okay. So now let's rewrite this limit using all of that information. So we have the limit as capital N goes to infinity of, let's see, h 2m capital N minus 1, and then minus half h little n capital N, that'll be that term, and then over here minus half h lowercase m capital N, that'll be from that term right there. And notice that I've spread these out, and that's because I'm going to add a really fancy version of 0 that will allow us to use this limit right here. So here I'll subtract the natural log of, let's see, 2mn minus 1. And here I'll add in the natural log of little n times capital N. And then finally here I'll add in 1/2 the natural log of m times capital N. But now since I've added and subtracted those things in, that means I need to subtract and add them so that nothing changes. So let's do that here. So we're also going to do plus a natural log of 2mn minus 1 to counteract that. And here we'll do minus 1/2 natural log of n capital N to counteract that. And then another minus 1/2 natural log of m capital N to counteract that. Okay, great. But now here's where the magic happens. So notice that this object right here, as capital N goes to infinity, will go to gamma by this limit that we have here. So this is going to go to gamma. And then likewise, these two terms right here will go to minus 1/2 gamma. And then these two terms right here will also go to minus 1/2 gamma. But we've got gamma minus 1/2 gamma minus another 1/2 gamma. Those cancel, meaning that all we have is the limit of what's going down there in that magenta. Okay, so let's bring that limit up, and then, we're pretty much done. So I've taken where we were on the last board, and I've factored 1/2 out, leaving us with the following limit. Let's recall that a bunch of stuff canceled kind of magically. Okay, so now let's finish this thing off. So the main tool here will be to use logarithm rules to push all of those logarithms together. So let's see, that'll give us the natural log of 2m capital N minus 1 all squared. That's just from multiplier becomes an exponent over, let's see what we'll have. We'll have m times n times capital N squared. Okay, but then let's see. This numerator will multiply out to 4 times m squared times capital N squared, and then plus lower terms. And those lower terms won't matter because inside of the limit, they'll just go to 0 given what's happening in the denominator right there. So all we have to worry about is what's happening with these highest order terms, so that and that, but now our capital N squared will cancel, and then this m will cancel that exponent there, and we'll be left with 1/2 the natural log of 4m over n. But that's maybe not the standard way to write this. The standard way to write this would be the natural log of 2 plus 1/2 the natural log of m over n, which you can get just by applying logarithm rules again. So that's what we get. That's what we get for this rearrangement of the alternating harmonic series. So it's a nice closed form. Also, it gives credence to this kind of structure that we have over here, where natural log of 2 is like our starting point, and any rearrangement is some sort of tweak of that starting point. Okay, so thanks for sticking around. If you're still around, maybe consider subscribing. It would really help the channel out, and that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.